Okay, so to explain or to back up our analysis, in the previous video, we talked about the introduction of fluid flow through a pipe, talking about all the energy losses that takes place whenever fluid flow through pipes. And we said we have two major energy losses, the major energy loss and the minor energy loss. So we are going to use this particular problem now to actually explain what that concept we learned in the previous video is all about. All right, so if you're new to this video, please do well to watch the previous video on introduction to energy flow through pipes to get everything in details. All right, let's consider this question on the board. The question says two reservoirs are connected by a pipeline containing of two pipes, one of 15 centimeter diameter and length 6 meter, and the other of diameter 22.5 and 16 meters length. If the difference of water level in the two reservoirs is 6 meters, question says calculate the discharge and draw the energy gradient line. All right, so we are given the pipe. This is a reservoir that contains water. Now, the question is saying that the height difference in level, when they say difference in level, they simply means height. The difference in level between the two reservoirs is 6 meters. So the height of fluid flow between the reservoir and the pipe is simply 6 meters as indicated here. So we have two pipes, pipe 1 and pipe 2, connected together, which is jointly connected to this particular reservoir. Now, the length of the first pipe is 6 meters. So which means this is the first pipe. Length from here to this point is 6 meters. And the length of the second pipe is 22.5 as indicated there. Okay, sorry, is 16 meters as indicated there. So length of the second pipe is 16 meters. So you have something like this, 16 meters. All right, we were also given diameter. Diameter of the first pipe is 15 centimeters. So we need to convert this to meters. D1, which is diameter of the first pipe, is 15 centimeter, and that's simply 15 divided by 100, which will give us about 0.15 in meters. So the first diameter is 0.15 meters. So D1 equals 0.15 meters. The second diameter was given as 22.5 centimeters. So D2 is 22.5 divided by 100, and that will give us about 0.225 in meters. So D2 equals 0.225 in meters. So these are the first things to do. Pick out all your parameters. So we have the diameters D1 and D2. We have their lengths L1 and L2 for each of these pipes was given, but we don't know the velocity. Now take note, we are given friction factor. Take F to be equal to 0.04. All right, so it has already been given to us, so there's no need to solve for the value of F. The question is asking us to find the discharge and also calculate also draw the energy gradient line. But you cannot draw the energy gradient line without solving for the whole energy losses, because it is the value of the energy losses that we use to draw the energy gradient line, and if possibly the hydraulic gradient line as well. Similarly, you're asked to find discharge. You cannot also find discharge without knowing their velocities. It's very easy, you know the diameters, you can compute the areas of the pipe, but then what are the velocities? You can't solve without them. So that is where we have to now employ all the ideas we learned in the previous video to solving this problem. Now, the first thing to do, like I said, you recall from Bernoulli's equation. All right, from Bernoulli's equation, we had that P1 all over, okay, that's pressure head plus kinetic head, V1 squared over 2G plus potential head, Z1 is equal to pressure head at the outlet, P2 all over W plus kinetic head, V2 squared over 2G plus Z2 plus the sum of all losses, okay, plus the sum of the entire losses in the pipeline. All right, but in this question, we weren't given inlet pressure or the outlet pressure. It wasn't given to us. So automatically, this is 0. Since pressure is 0, this is also what? 0. P1 was not given. P1 is equal to 0, and that's also equal to P2. So which means this and this automatically becomes 0. So from the Bernoulli's equation now, all we have is simply V1 all squared over 2G plus Z1, okay, equals V2 squared over 2G plus Z2 plus losses, okay, plus all losses. All right, now let's bring every other terms here together and keep the losses aside. Let's bring every terms here together. We are going to have V1 all squared over 2G. Okay, so if V2 squared over 2G comes here, it becomes negative. So you have here minus V2 squared all over 2G. Okay, plus here you have Z1. Bringing Z2 over here, you have Z1 minus Z2. Okay, and this is equal to all losses that you have there. Now, take note, Z1 minus Z2 is what? The difference in level between the reservoirs, which the question told us that the height level is what? 6 meters. So Z1 minus Z2 becomes difference in level between the two reservoirs. So Z1 minus Z2 is simply 6 meters. Therefore, Z1 minus Z2 equals 6 meters. That's the difference. Z1 minus here connotates difference. So Z1 minus Z2 is equal to 6 meters from the question. Hence, you have that. Hence, you have that. Okay, also from here you can make a take the LCM here. LCM here is 2G. So you simply have 2G into this becomes V1 all squared minus V2 all squared plus. So in place of Z1 minus Z2, we simply have what? 6. And this is equal to all the losses. Okay, so our aim now is to find the values of all the losses. So let's call this equation 1. Now, what are the losses involved? Or before going into the losses, before going into the losses, recall that discharge, because the question has said we should find the discharge. Discharge Q is equal to area times velocity. So, but from continuity equation, not forgetting, from continuity equation, discharge is same all through the pipe. So discharge at this point equals discharge at this point. From continuity equation, you have that Q1 is equal to what? Q2. Discharge at section 1 equals discharge at section 2. And that simply means, Q1 itself is area 1 times velocity 1, and Q2 itself is simply area 2 times velocity 2. So if from continuity equation the discharges are equal, this simply implies that area 1 times velocity 1 is equal to area 2 times velocity 2. So since we don't know the velocities, it means we have to solve them in terms of one another. So we can solve V1 in terms of V2, or you can solve V2 in terms of V1. But then let's solve V1 in terms of V2. Okay. So this means that V1 is equal to A2 V2 all over A1. So let's find these areas now, where A1 is equal to pi over 4 times diameter 1 all squared. So this is equal to pi remains 3.142 times diameter of pipe 1, D1 was given to us as 0.15 meters. So you have times 0.15 meters all squared all over 4. So A1 is now equal to, please give me 3.142 times 0.15 squared. So you have 0.0706 divided by 4. Divided by 4. So A1 becomes, the first area is 0.0 what? 0176 in meter squared. So this becomes the value of the first area. Similarly, to calculate the second area, A2 is equal to pi diameter 2 squared all over 4, and this is equal to, pi is a constant value, 3.142 multiplies, the second diameter was given to us as 0.225 meters, so multiply by 0.225 all squared divided by 4. Okay, so give me a2 is equal to, give me pi 3.142 times 0.225 all squared. We have 0.15991 divided by 4. So this simply implies that A2 is equal to 0.0397 meter squared. So this is now the second area. So we have area 1, we have area 2. We cannot impute that into this value, this equation, to obtain the value of the first velocity in terms of the second velocity. All right, so I'm going to wipe this portion of the board. So help me keep this in mind. The value of the friction factor, let me put it down here. F was given as 0.04. All right, also keep the question in mind. Question says we should calculate the discharge and also draw the energy gradient line. So I'll just wipe this portion of the board and leave the pipe. All right, so from here now, we'll find that V1 is equal to A2 over A1, or A2 times V2 all over A1. So we can actually constitute or compute the value of V1. So let's do that over here. V1 equals A2 V2 over A1, and that is equal to A2. What is A2? A2 gave us 0.0397 multiplied by V2 all over A1. What's A1? You have 0.0176 for A1. So give me this division. This simply implies that V1 is equal to 0.0397 divided 0.0176. So you have 2.25 V2. So this becomes the value of velocity V1 in terms of V2. Having known this now, we can now start calculating the energy losses. Now, the first energy loss, like I told you, is when the fluid enters into the pipe, it encounters what is called energy loss due to what? Entrance. So we calculate entrance energy loss, or energy loss due to entrance, and we gave the formula in the previous video as I for inlet is equal to 0.5 depending on the speed of flow. In this case now, the speed of flow is V1 because it is this same fluid that enters, which is the initial speed of flow. So it becomes 0.5 V1 all squared all over 2G. That's the formula to calculate that. Okay, so this is now equal to 0.5. V1 is unknown, but we're able to relate V1 to V2, and we obtain 2.25 V2. So in place of V1, we have times 2.25 V2, remember, all squared, because this is V1 squared, divided by 2, G remains 9.81, gravity, that's constant. So entrance head loss, or entrance energy loss, HI, is now equal to, this is now 0.5 multiplied by, please give me 2.25 squared. You have 5.063 V2 all squared divided by 2 times 9.81 is 19.62. So this is equal to, give me now 0.5 multiplies 5.063 divided by 19.62. So this implies that the entrance energy loss is 0.12 what? Okay, so 0.13, approximately 0.13 V2 all squared. So you can keep this aside. This is the first energy loss calculated. Now, the next energy loss, as the fluid enters into the pipe, like I told you in the previous video, there is bound to be what? Contact between two surfaces. That's friction. Whenever two surfaces come in contact with one another, there is bound to be friction. So the fluid enters into this pipe and touches the surface of the pipe, then there is bound to be friction. So that friction will reduce the intensity or the energy of flow in the fluid. That will give rise to what is called the energy loss due to friction. Energy loss due to friction. So like I said in that previous video, that fluid flow in a pipe constitutes different forms of energy, the major energy and the minor energy. So the energy loss due to friction is a major energy loss. Okay, energy loss due to friction is a major energy loss, whereas the energy loss due to entrance is a minor energy loss. And this can be obtained HF using the Darcy-Weisbach equation, which is simply 4 times FL times V squared all over D times 2G. Now, what is V? V becomes the speed of flow of the fluid in that particular section. Since we are on section 1, which is V1, so V becomes V1 squared. And also, diameter becomes diameter of that particular section pipe, which is also what? D1. So this is now D1. So this becomes the formula to calculate the head loss due to friction as the fluid flows through the pipe. So we can do this by HF is equal to 4 times, remember friction factor was given to us as 0.04, so multiply by 0.04 multiply by the length of that particular pipe remains L1 now. So we're still on pipe 1. The length of pipe 1 is 6 meters. Multiply by 6. Multiply by the speed. The speed of pipe 1, V1, is unknown, but we obtained it here as 2.25 V2. So simply multiply by 2.25 V2. But remember, this is V1 squared. So you have to square this. All squared. Divide by diameter of that pipe, and diameter of pipe 1 remains 0.15. So divide by 0.15 multiply by 2G. 2G remains 9.81. Okay. Let me switch the camera. So head loss due to friction, HF, is now equal to, give me 4 times 0.04 times 6. 4 times 0.04 times 6. You have 0.96 multiplied by, now you give me 2.25 squared. 2.25 squared give us 5.06 3 V2 all squared, divide by, give me 0.15 multiplies 2 multiplies 9.81. You have 2.943. Okay, so head loss due to friction is now equal to, now you give me 0.96 multiplies 5.063 divides 2.943. So you have HF to be equal to 1.65 V2 all square. So this becomes the head loss due to friction, and that is a major energy loss. Now, as this fluid flows and gets to this point, it encounters an increase, a sudden increase in the pipe. So which means this fluid has to adjust to fill up all this other portion. It has to adjust to fill this portion before it starts moving ahead. So that will slow the speed of the fluid down, and that will constitute to what is called the head loss due to sudden enlargement of the pipe, because the diameter of the pipe here is smaller compared to the diameter of the pipe here. This is larger than this. So for that reason, the fluid speed will reduce in size, and that will also reduce the energy of the fluid. So that will constitute to what is called the third energy, and we have the energy loss due to sudden enlargement. So we talked about all this in the introduction video. Please do well to watch it. Sudden enlargement. And the formula to calculate that, we said energy loss due to enlargement, HE, is given as V1 minus V2 all squared divided by 2G. That's the formula to calculate it. So this is now equal to, we know what V1 is. We solve for V1 in terms of V2 and we obtain 2.25 V2. So in place of V1, we have 2.25 V2 minus V2 all squared all over 2 times 9.81. G remains 9.81. So head loss due to enlargement is now equal to 2.25 minus V2. 2.25 V2 minus V2 will give us 1.25 V2 all squared divided by 2 times 9.81 will give us 19.62. So this is now equal to, give me 1.25 all squared. So squaring everything here now, 1.25 squared, you have 1.563. Remember, V2 becomes V2 all squared all over 19.62. So head loss due to sudden enlargement becomes 1.563 divides 19.62. You have 0.07, okay, 0.080, okay, this can go 0.080 V2 all squared. So this becomes the head loss due to sudden enlargement. All right, so notice notice that as the fluid enters into this pipe as well, there is now a contact between this fluid and the walls of the pipe. As the fluid enters into the pipe, there is now a contact between the fluid and the walls of the pipe. That will also constitute another major energy loss, which is called energy loss due to friction, because the fluid surface is in contact with the pipe surface, and that will reduce the motion as well of the fluid, giving rise to energy loss due to friction. So we also have to calculate the energy loss due to friction at this particular pipe using Darcy-Weisbach equation. So the third or the fourth major energy loss we're going to calculate now becomes energy loss due to friction at that particular pipe segment. Okay. All right. So I'll wipe here. I will need equation 1. So I'll just wipe the top surface. So I'm keeping equation 1 because I will need the equation. So with the fourth energy loss we'll calculate is also energy loss due to friction at pipe 2. Okay, due to friction at pipe 2. We also employed the Darcy-Weisbach equation HF2. This is now HF2, and that's equal to 4FL times V squared all over D times 2G. Now, since we are at pipe 2, it means diameter we are going to be considering becomes diameter 2, which is diameter of pipe 2. So this becomes D2. Also, the velocity we are going to be considering now also becomes V2 all squared. And the length becomes length of pipe 2. So you have this. Hence, head loss due to friction at pipe 2 is now equal to force 4 times friction factor was given in the equation as 0.04. So multiply 0.04 times length of pipe 2 is given as 16 meters. Multiply by 16 meters times V2. Okay, so since we'll be solving all the energy losses in terms of V2, let's also keep V2 as V2. So we have times V2 all squared all over D2. Diameter 2 was given as 0.225. So you have 0.225 multiplied by 2 times 9.81. So head loss due to friction at pipe 2 is now equal to, give me 4 times 0.004, 4 times 0.04 times 16, please. 4 times 0.04 times 16. You have 2.56 V2 all squared divides by, give me 0.225 multiplies 2 by 9.81. 0.225 multiply 2 multiply 9.81. You have 4.41 0.445. So give me 2.56 divides 4.4145. 0.97. So 979. Okay, 5. So you have 0.58. You have 0.58 V2 all squared. So this becomes the energy loss or head loss due to friction in pipe 2. So notice that after calculating the energy loss due to friction, now the fluid, this pipe does not contain a bend. This pipe does not contain a bend, so you cannot calculate for energy loss due to bend. There's also no obstruction in the path of fluid. There's no obstruction in this pipe, so you cannot calculate energy loss due to what? Obstruction. That becomes 0. There's also no fitting in this pipe. There's no type of fitting here on this pipe, so you cannot calculate energy loss due to what? Fitting. Those energy losses are 0 since their conditions are not included in the piping system. That means the only energy loss now is at the end of the pipe. As the fluid flows up to this point, what happens? It exits the pipe. The fluid exits the pipe. Okay, as the fluid flows up to this point, it exits the pipe, giving rise to what is called the energy loss due to what? Exit. Energy loss due to exit. So that's the next energy loss we are going to calculate. So I will do it over there. I'll flip the camera now. All right, so finally we calculate the head loss due to exit. Head loss due to exit. That should be the sixth. Head loss due to exit or energy loss, whichever one can go, head loss or energy loss due to exit. Head loss due to exit, and the formula is simply HO, O for output or outlet, is simply V squared all over 2G. That's the formula to calculate the head loss due to exit. But now you consider V there becomes the velocity at the point of exit, and the velocity at the point of exit here is simply V2. So you simply put in V2 all squared. 2, this is 3. Okay, this is number 5. All right, so this is the fifth energy loss phase. Energy loss due to exit. So that's the formula to calculate it. So since the exit point is, or exit speed is V2, we simply make use of V2 as that velocity there. So you have V2 squared all over 2G, and that's equal to, now once again, since we're solving all the head losses in terms of V2, then we still leave V2 to be V2. So this becomes V2 all squared all over 2 times G is 9.81, which is equal to V2 all squared divides 19.62. Of course, 2 times 9.81 gives us 19.62. So this is simply saying 1 divided by 19.62. This implies head loss due to exit is now equal to. So give me 1, you have 0.05 V2 squared. All right, so this becomes head loss due to the outlet. So in all, we've calculated all the head losses. So let's now substitute them into what? The Bernoulli's equation. Now, in the Bernoulli's equation, remember we had, okay, I've wiped this side. We had V1 squared minus V2 squared all over 2G plus 6 equals all the losses. This is what we obtained in equation 1 earlier. So please confirm this again. But I think it's correct. V1 squared minus V2 squared all over 2G plus 6. And that's equal to all the losses. Now we found all the losses. We can now impute all of them into this equation. Substituting losses into equation 1. So in equation 1, we had V1 minus V2 squared, V1 minus V2, okay, V1 squared minus V2 squared all over 2G, okay, plus 6, and that's equal to, now, all the head losses that we obtained from the very first, we obtain head loss due to entrance, head loss due to entrance, and we obtain 0.13 V2 squared. So this is simply going to give us 0.13 V2 squared plus the second head loss is head loss due to friction. We obtain head loss due to friction as 1.65 V2 squared. That's friction in the first pipe. That's 1.65 V2 all squared plus the third head loss we obtained was head loss due to sudden enlargement of the pipe, and we obtained that head loss to be equal to 0.08 V2 squared. We obtain that to be 0.08 V2 all squared plus the fourth head loss was head loss due to friction in pipe 2, and we obtain this to be equal to 0.058 V2 squared. This is 0.058 V2 squared plus the final energy loss we obtained was outlet energy loss, which gave us 0.05 V2 squared. So plus 0.05 V2 all squared. So, but not forgetting as well that we said earlier or we calculated earlier that V1 is equal to 2.25 V2. V1 equals 2.25 V2. So, which means in place of this V1 squared, we can replace it with what? 2.25 V2 all squared minus V2 squared, which is here, minus V2 squared all over 2G. So this becomes 2 times 9.81. Remember, put down your plus 6, and that's equal to now. Let's add up all the energy losses. We have 0.13 plus 1.65 plus 0.08 plus 0.058 plus 0.05, 0.013, 0.13 please, 0.13 plus 1.65 plus 0.08 plus 0.058 plus 0.05. Okay, so you have 1.968 V2 all squared. So this becomes the sum of the entire energy losses, 1.968 V2 all squared. Now from here, 2.25 squared, let's square this term now. 2.25 squared is what? We have 5.063. Remember V squared as well. V2 squared minus V2 squared here, all over 2 times 9.81 gives us 19.62 plus, put down your 6, and this is equal to 1.968 V2 squared. So you have this. Now, we now obtain 5.063 minus V2. Okay, 5.063 V2 squared minus V2 squared. That will give us about 4.063. All right, so obtain the value of we obtain the value of 5.063 minus 5.063 V2 squared minus V2 squared will give us 4.063 V2 squared all over 19.62 plus 6, and that's equal to the sum of the losses, 1.968 V2 squared, 1.968 V2 all squared. So give me 4.063 divides 19.62. So you have 0.21 V2 squared plus 6 equals 1.968 V2 squared. So let's make all the terms in V2 subject or related. So simply send 0.21 V2 squared over here, leaving 6 here. Therefore, we have 6 is now equal to 1.968 V2 squared minus, of course, this cross here becomes negative, minus 0.21 V2 all squared. So we have here 6 is equal to 1.968 minus 0.21. So we have 1.758 V2 squared. All right, so from here, to make V2 squared is now equal to 6 divides 1.758. So this simply implies that V2 squared is equal to 6 divides 1.758. That's 3.41. All right, but this is now V2 squared. We need to find V2. We simply take the square root of this value to obtain V2. Therefore, V2 is equal to the square root of 3.41. This implies that V2 is equal to what? Square root implies V2 is equal to square root of 3.41 is what? 1.8, right? 1.8 meters per, okay, 1.84 meters per second. 1.84 meters per second. So this becomes V2. So if we know V2, it means we can find V1 from here. Okay, so recall that V1 is equal to 2.25 V2. So that means this is equal to 2.25. V2 is 1.84. So 2.25 multiplies 1.84. This implies that the first speed, V1, is equal to, you have 4.14 meters per second. So this becomes the first velocity, and it's very obvious the velocity at a very smaller diameter is quite higher, should be higher than the velocity at a larger diameter. So which is why when it entered here, due to this sudden enlargement, there was a loss of energy. And it's clear from here, V1 is bigger than V2, as can be seen. But the question itself says we should calculate the discharge. Okay, so if we know this now, we can calculate the discharge, and then we can calculate for all the energy losses that we have. But let's just solve for the discharge. We can do it over here. I will leave this equation for the energy losses. Okay, so let's solve for the discharge over here. The first question says calculate discharge, and we know that Q can either be A1 V1 or it can also be A2 V2. So this simply implies that Q is equal to, what was our first area? 0.0176. So recall that A1 gave us 0.0176. A1 gave us this value, multiplied by V1. We obtain V1 here as 4.14. So multiply by 4.14. This simply implies that Q is equal to 0.0176 multiplies 4.14. You have 0.072 in meter cube per second. So this becomes the discharge through the pipe. But just to confirm, like I said, it's also A2 times V2. So you can also find using A2 V2, and that's equal to A2 gave us, we saw for A2 earlier, we obtained 0.0397. So A2 is 0.0397 multiplied by V2. We obtain V2 here as 1.84 multiplies 1.84. So this implies that this charge is equal to, so you have 0.073, okay, which is not bad, still the same, meter cube per second. So simply just approximation errors, but then comparing the two, they are the same. That's the idea behind continuity equation. So that's the first question answered. The second question says we should draw the energy gradient line, but you can't draw the energy gradient line without knowing the values of the energy losses. So we need to now put in the values of V2 that we obtain into all the energy equations to now obtain the energy losses. So I will make out a space for that. Okay, I think I should make out this space. All right, so not forgetting V2 is 1.84. So the first energy loss was energy loss due to entrance, HI, and we obtain HI as 0.13 V2 squared is here. Hi is 0.13 V2 all squared. So this is equal to 0.13. V2 is 1.84 all squared. So give me this, all of them together. So this implies that Hi, entrance energy loss, is equal to, so just give me 0.13 multiplies 1.84 squared. So you have 0.44 in meters. Okay, that becomes the entrance energy loss. The next energy loss we did was energy loss due to friction at the first pipe, and we obtained the equation for that as 1.65 V2 squared. We obtained that equation as 1.65 V2 all squared. So this is equal to 1.65 V2 remains 1.84 all squared. So multiply everything all through. We have HF1 to be equal to, so we have 5.60 in meters. Okay, we have 5.60 in meters. That becomes head loss due to friction. The third energy loss we calculated was energy loss due to sudden enlargement in the pipe, and we obtained that equation to be 0.08 V2 squared. We obtain it to be 0.08 V2 all squared, and that's equal to 0.08 V2 remains 1.84 all squared. Okay, so energy loss due to sudden enlargement is 0.27 in meters. Okay, let's call that 0.30, 0.3 in meters, just approximate. You have 0.3 in meters. That becomes energy loss due to sudden enlargement. The fourth energy loss we did was energy loss due to friction in the second pipe. That's HF2, and that is equal to, okay, so HF2 is 0.58 V2 all squared. So this is equal to 0.58 V2. V2 is 1.84 all squared. So this implies that head loss due to friction at the second pipe is equal to, multiply all through for me. You have 1.96. Okay, 1.96 in meters. So this is head loss due to friction at the second pipe. And finally, we calculated the outlet energy, or energy due to exit, which is HO, and we obtained the value as 0.05. H will give us 0.05 V2 all squared, and that is equal to 0.05 V2 remains 1.84 all squared. So this implies that HO is equal to, multiply all through, 0.05 multiplies 1.84 all squared. So you have 0.17 in meters. So this becomes the outlet energy. All right, so these are all the values of the energy losses. We can now use them to draw the energy gradient line. So I will still do it on this diagram. I will do it on this diagram. So it's best to always draw, if you want to draw the energy gradient line, you draw it on the diagram is best. Quite okay that way, to draw it from the given diagram. Now, the first energy loss was entrance energy loss, and entrance energy loss is 0.4. So how to draw it? The entrance, of course, this is the entrance. It starts from here and enters into the pipe. So you measure out, this should be your maximum. The point where the fluid level stops should be your maximum point. So from here, you trace out a line. If you want to, faint line, measure out 0.4 with your meter rule. Okay, to be, if you want to be more accurate, you can use a graph sheet. So you measure out 0.4. I will have something or somewhere around here. This is 0.44 meters, and that is HI. Okay, so you can trace this point also. You can trace this point out if you wish with a faint line. Okay, the next energy loss is energy loss due to friction, and energy loss due to friction gave us 5.6 meters, 5.60 meters. All right, so you measure out 5.60. So you target at this edge of the pipe. You target at the edge of the pipe and you measure out 5.60. So of course, you know that 5.60 happens to be the largest there. So this is 0.4. You can of course extend 5.60 to be somewhere around. It happens to be the largest. So this could be 5, which is HF1, 5.60 meters. Now, once you pick up 5.60, what you do is join this point 0.04 with a meter rule. Join these points to what? These points. You join these 2 points together. Okay, so from the entrance level down to what the energy to the head loss due to friction, you join the two of them together and you stop there. The next energy loss was energy loss due to sudden enlargement of the pipe, and we obtained 0.3 meters for it. So you measure now due to sudden enlargement of the pipe. So that's why you have to target here, okay, where the enlargement took place, to measure out 0.5, which is energy loss due to friction. Now, you measure out 0.3. 0.3 should be from here to this point. Also, measure out 0.3 from here to this point, and then you join these 2 points together. Measure at 0.3. Now, this is now head loss. Okay, if you trace this point out, this is head loss due to sudden enlargement, 0.3 meters. So you join these 2 points together, you have this. That's the enlargement. So you're seeing that we are reproducing almost what we have in the original diagram. So it becomes head loss due to sudden enlargement, and you have that. So it ends in this place. So you can trace this point out somewhere around here. You can trace it out. And next is exit. The head loss due to, okay, next is head loss due to friction at pipe 2, which gave us 1.96. So you can measure that. Head loss due to friction, remember this was the datum line for 0.3, which we measured from there to this point. Now you can now measure at 1. Okay, you can measure somewhere. This is not accurate scaling, please. I'm using a freehand sketch. So this is now head loss due to friction at pipe 2, which is 1.96, approximately 2. So you join this point again, this point now, you join these points to the head loss. Okay, one should have some measures down. Okay, so you join this point again to that point. You have this. Okay, join this point to that point. Let me take off these diagrams. So you join this point, okay, with a meter rule to that point, okay, which is here. So this is the head loss due to friction. So you have this. So this becomes the energy gradient line. This line can call here A, call here B, call here C, call here D. This is called the energy gradient line. Line A, B, C, D is simply the energy gradient line, EGL. That's the energy gradient line. So if you're asked to draw the hydraulic gradient line, it's quite simple. You take the measurement, you can just simply measure 1 meters. You can take an accurate scale. That one does not have any measurement. You can take an accurate scale, just take like a scale of 1 meters. Okay, take a scale of 1 meters from where it ends. That's from this point D, where it ends. Take a scale of 1 meters, measure somewhere here, and you have something like this. Then you reproduce the lines you have. These lines now, reproduce these lines, okay, but the other way round. You produce this line the other way round with a faint line. So what does that mean? I'm going to retrace this particular line now, but with a faint line, okay, or broken lines. You can use a broken line, but it has to be as accurate as possible. You have to try to make it as neat as possible. So you retrace these lines with a broken line. Okay, you trace the lines with a broken line. So I've reproduced these points. Notice now that here there was an enlargement which came down from the hydraulic gradient line. Also, you also what come down, okay, you also come down, something like this, and then you produce this particular line as well with a broken line. So you have something like this. So it's usually joined together. You have something like this. So these lines are called the hydraulic gradient line. So you can, of course, it doesn't have an accurate measurement. So you can simply take a scale of 1 meters, but then you have to reproduce everything on the energy gradient line beneath. So they are called hydraulic gradient line. So you can scale this, or you can label this. This is A to D. You can label this E, F, and G, E, F, G, okay, and H. So line E, F, G, H give us a hydraulic gradient line. So that's how to draw the energy gradient line and the hydraulic gradient line. All right, guys, the video has already become too long. I hope you find this video interesting and helpful. Please, if you do, I would like to get your thoughts in the comment section. And of course, if you have any question at all to ask, also do well to post in the comment section, and I promise to respond to all your questions. I will see you in next video with another amazing question on energy gradient lines and hydraulic gradient lines, and of course energy losses in pipes. Thanks and cheers.